The objective of this lecture is to provide the first part of the study of the kinetics of a system of particles. So the starting point for this lecture is as follows, is let P1 through Pn be a system of particles with masses m1 through m sub n respectively. Furthermore, let I be an inertial reference frame and let O be a point fixed in I. And finally, let Ri, I equals 1, be the position of Pi, again, I equals 1, measured from point O. In other words, what we're saying is that Ri is the same thing as Ri relative to O. But we're not going to actually use that notation Ri relative to O. We're going to use this shorthand. So, given that setup, here's what the picture looks like. We have an inertial frame. Could call that inertial frame I. We have a point O, and O is fixed in I. And we have a bunch of particles whose positions are all measured from point O. And I'm going to call these particles, these positions R1, this is M1, R2, and this is M2, and so on, M3, and then R3, and then finally all the way down to R sub n, and then this is M sub n. Now, using the setup, we're going to define the following quantities. So let Vi in I be the velocity of Pi as viewed by an observer fixed in the inertial frame I, and let Ai be the acceleration of Pi as viewed by an observer fixed in I. And for these two, we've got I going from 1 to n. Now, given these definitions, we're going to apply Newton's laws to each particle in the system. So next, let Ri be the resultant force acting on pi, and again, I goes from 1 to n. The resultant force, Ri, can be decomposed as follows. Ri is equal to Fi plus the sum from j equals 1 to n of Fij, where Fi is the resultant external force acting on pi. And when I say external, I mean external to the system. And Fij is the force exerted by particle j on particle I. Now, you can see that every other force in the system exerts a force on particle I. And in order for this to make any sense beyond that, we note that Fii is equal to 0, which means a particle cannot exert a force on itself. So now, let's take this one step further. So in this study, it is assumed that Fij lies along the line of action between Pi and Pj, which means this is if I have m sub I and I have m sub j, then the force exerted by particle I on particle j lies in this direction. And this assumption, or this assumption, together with the facts, so together with the fact that Fji equals minus Fij, the forces of interaction between the particles satisfy the strong form of Newton's third law. Now, Newton's third law says that for every action there's an equal and opposite reaction. But it doesn't say anything about the line of action along which the forces lie. In this particular case, Fij is in the equal and opposite direction as Fji. So Fji is equal to minus Fij, but there's also the additional assumption that these forces lie along the lines of action connecting Mi and Mj. So that's what's called the strong form of Newton's third law. Now, once we have that, we have the setup for the remainder of this discussion. So then, from Newton's second law, we have that the resultant force acting on particle I has to equal the mass of I times the acceleration of I in the inertial frame. if we substitute the resultant force, we get that the resultant external force plus the sum of the forces of interaction has to equal the mass of I times the acceleration of I in the inertial frame. So you can see here that I substituted in Ri, and Ri was defined as the force that I described earlier. So now suppose we sum across all particles. Suppose now that the sum is taken across all particles in the system. Then the sum from I equals 1 to n of Fi plus the sum from j equals 1 to n of Fij has to equal the sum from I equals 1 to n of mi times the acceleration of each particle in the inertial frame. So that gives that the sum from I equals 1 to n of Fi plus the sum from I equals 1 to n of the sum from j equals 1 to n of Fij has to equal the sum from I equals 1 to n. Let's write that a little bit more. Sum from I equals 1 to n of mi times the acceleration in the inertial frame. Now, because Fij equals minus Fji, or vice versa, the double sum from I equals 1 to n and j equals 1 to n of Fij equals 0. So therefore, the summation from I equals 1 to n of Fi has to equal the summation from I equals 1 to n of mi, ai, and I. Now we're going to define some new quantities. Now, I'm going to call this quantity r bar equal the summation from I equals 1 to n of mi, ri, all divided by the summation of mi. And this is going to equal the summation of mi, ri from I equals 1 to n, all divided by m, where I'll define what m is. And this quantity is what's called the position of the center of mass of the system, and the summation of mi from I equals 1 to n is equal to m, which is what's called the total mass of the system. Now, from this we can actually define two other quantities. V bar I is equal to the rate of change of r bar I, which is equal to the summation of mi, vi, and I going from 1 to n, all divided by m. And the acceleration, we're going to call it a bar I, is equal to d dt in I of v bar I, which is equal to the summation from I equals 1 to n of mi, ai, and I, all divided by m. Now these quantities, v bar I, is what's called the inertial velocity of the center of mass of the system, and A bar I is what's called the inertial acceleration of the center of mass of the system. Now, if we actually substitute in the last result, which is the acceleration of the center of mass, you can actually see that m a bar I equals the summation from I equals 1 to n of mi ai in I. So therefore, the summation from I equals 1 to n of fi equals m a bar I. And now finally we're going to let f equal the summation from I equal 1 to n of fi, which is equal to the resultant external force acting on the system which implies that F equals m times a bar I. Now this looks like Newton's second law, but it's actually not Newton's second law. It's a derived result. It basically says that the sum of all the forces external to the system is equal to the mass times the acceleration of the center of mass of the system. It's the first result that in kinetics of a system of particles that is actually used when analyzing multiple systems with multiple particles. So in order to be able to show how this result is actually used, let's consider the following example. Let's do an example straight away to be able to understand the manner in which this is used. So this example is as follows: is that we have a wedge which slides on a horizontal plane, and this wedge is triangular shaped, and it has a wedge angle which I'll define as beta. Beta is a constant. And the position of the wedge is measured from a point fixed in the inertial frame, and the displacement is x1. Sliding on the wedge is a block. Now this wedge has mass m1. This block has mass m2. And now there's a point that's fixed to the wedge, which I'll just denote this point as q. And the displacement of the block is measured relative to the wedge, and that displacement is x2. Now we're going to assume here that gravity acts downward, and we're also going to assume no friction. So when I mean no friction, there's no friction anywhere in the problem. And of course, in that case, this means no friction relative with the ground contact. It also means no friction at the point where the block meets the wedge. So the objective is going to be to derive the differential equations of motion. Is derive the differential equations of motion for the system. And the first part of this is going to be to do the kinematics, and then we're going to do the kinetics. So let's do the kinematics first. We have to describe here the motion of both objects, both the wedge and the block. So we're going to use two reference frames, even though there's no rotation, and I'm going to explain that in just a minute. The first frame is going to be the inertial frame, and I'll denote that I. And And the second reference frame is actually going to be the wedge. And I'll denote that W. The coordinate system that's fixed in the inertial reference frame is going to have its origin at O. I'm going to put big EX to the right. I'm going to put EZ into the page, and then EY is going to equal EZ crossed with EX. For the coordinate system fixed to the wedge, you notice that I defined a point there called Q. So Q is fixed to the wedge. That's what I had said earlier. So I'm going to put the origin at Q. I'm going to say little ex is down the incline. I'm going to say little ez is equal to big Ez, and little ey is equal to Ez crossed with Ex. Now this picture looks as follows, is that big Ex points to the right, big Ez is into the page, and big Ey is equal to Ez crossed with Ex, which is down. Little ex points down the incline, and then little ez is equal to big Ez, and the little ey is equal to Ez crossed with the x. And if you want to be a little bit more careful about this to make it look like 90 degrees, we'll draw it as such. Now, given the fact that if you look at the picture back here that the angle beta is defined as I've given, this angle is beta, and then this angle is also beta. Now what we have to do is we have to describe the position of each object in the system relative to an inertially fixed point. So the position of 1, which is the position of the wedge, and again, this is relative to O, because O is our inertially fixed point, is equal to x1 Ex. So from this we immediately get that the velocity of the wedge is x1 dot Ex, and the acceleration of the wedge is equal to x1 double dot Ex. So next we need the position of the block. And again, we need to measure the position of the block relative to O, because O is our inertially fixed point. So this is equal to the position of the wedge plus the position of the block relative to the wedge, which is equal to x1 Ex plus x2 times little ex. So therefore, the velocity of the block is equal to x1 dot Ex plus x2 dot little ex, and if I give myself a little bit more space here, it's equal to x1 dot Ex plus x2 dot little ex, and then the acceleration of the block is equal to x1 double dot little ex, big Ex plus x2 double dot little ex. Now we have all the kinematic quantities that we need in order to be able to move on to do the kinetics. So the kinetics are sort of the more complicated part of this problem, which is that it is necessary to analyze the appropriate systems and subsystems in order to determine the differential equations. Now, here are the possible systems. And what I'm going to draw here are the free body diagrams. So the first possible system is the wedge. And the free body diagram for the wedge is as follows. We have a normal force acting from the ground, and then we've got the force of gravity, and then we have the force exerted by the block on the wedge. I'm going to call that F12 because that's what we called it when we developed the theory. The second free body diagram, or the second system if you want to think about it that way, is the block. And the force exerted on the block, there are two forces exerted on the block. The first one is F21, which is the force exerted by the wedge on the block, and then M2 times G. The third system is the wedge plus the block. Plus block. This system looks as follows. We have the wedge, we have the block. The forces acting on this system are, again, there's the normal force from the ground, there's M1G, and then there's M2 times G. Now, when we look at this, you can see that the free body diagram of the wedge plus the free body diagram of the block equals the free body diagram of the wedge plus the block, because F21 is equal to minus F12. I'm going to put that in parentheses down here. So if I was to look at the force exerted by the wedge on the block, it's equal and opposite the force exerted by the block on the wedge. So if I add the two free body diagrams for the wedge and the block, I get the wedge plus the block. But the wedge plus the block is not going to give us enough equations to be able to determine a system of differential equations, because we need to determine two differential equations in this particular case, because there are 2 degrees of freedom in the system. One which is described by the displacement x1, and the other one which is described by the displacement x2. So what we need to do is we need to pick. So this is where systems of particles becomes a little bit tricky, is that we need to choose from the following free body diagrams. We need to choose either the wedge or the block, and use the system. And what I mean by the system is I mean the entire system, which is the wedge plus the block. So in this particular analysis, we're going to choose the following systems. 1, the block. And the reason we're going to choose the block is because it has fewer forces acting on it. And 2, the wedge plus the block. So let's look at the forces that are acting on each system. Let's look at the block. So we know that the force acting on the block has to equal the mass of the block times the acceleration of the block in the inertial frame. The force acting on the block, that's F2. This is the force on the block, is equal to, it's F, well, let's go back here. It's F21 plus M2 times G. Well, F21, since I don't know whether F21 acts in positive EY or negative EY, I'm just going to assume it's F21, and I'm just going to keep it positive, so it's EY. And then M2G is equal to M2G times big EY, because I define big EY to be down. So that says that F2 has to equal F21 little EY plus M2G times big EY. And that has to equal the mass of the block times the acceleration of the block in the inertial frame, but that's equal to the mass of the block times x1 double dot EX plus x2 double dot little ex. Now, from this equation, we get the following. We actually get that F21 EY plus M2G big EY is equal to M2 x1 double dot big EX plus M2 x2 double dot little ex. So now look what happens. If we want to get rid of this unknown, since F21 is unknown, take the scalar product in the direction of little ex. So then what we would say is F2 dotted with little ex is equal to M2 A2 and I dotted with little ex, which gives, well, if I take the scalar product in the direction of little ex, I get F21 little ey and then plus M2G times big EY dotted with little ex is equal to M2 x1 double dot EX plus M2 x2 double dot little ex dotted with little ex. And this gives, since little ey dotted with little ex is 0, it gives M2G ey dotted with little ex is equal to M2 x1 double dot big EX dotted with little ex plus M2 x2 double dot. Now you can actually see here that when we do this, we can now go back and we can figure out what EX is relative to little ex. So you can see that EX is equal to cosine beta times little ex minus the sine beta times little ey. So let's write that down. EX is equal to cosine of beta times little ex minus the sine of beta times little ey. So this says that big EX dotted with little ex is just equal to the cosine of beta. And then the same thing we can do for EY. EY is equal to, let's go back, and we can see that EY is equal to sine beta little ex plus cosine beta little ey. So that implies that EY dotted with little ex is equal to the sine of beta, which gives the first differential equation, M2G ey dotted with little x is sine beta, and that equals m2 x1 double dot, and then ex dot of big Ex dot with little ex is cosine of beta, and then plus m2 x2 double dot. This is the first differential equation. Now let's look at the system consisting of the block plus the wedge. So if you look, we started here with the block. So now we're going to do the wedge plus the block. Now this says the force acting on the system has to equal the mass of the system times the acceleration of the center of mass of the system. But remember that the mass of the system times the acceleration of the center of mass of the system is the sum of the masses multiplied by the respective inertial accelerations and then added together. Now, if we look at the force acting on this system, let's look at the free body diagrams. There's the free body diagram of the system. What do we have? We have N plus M1 plus M2 times G. But these forces both act in the EY direction. This is equal to N EY. Again, I'm not going to take into account the sign of N because I don't know what N is. But the force of gravity definitely acts in the positive EY direction. And that has to equal M1 times x1 double dot EX plus M2 times x1 double dot big EX plus x2 double dot times little ex. So now you can actually see that there's an unknown in here, and that unknown is n. So in order to get rid of n, we can take the scalar product in the ex direction. So in order to eliminate n, take scalar product in the ex direction. So what does that mean? That says that F dotted with EX has to equal the mass times the acceleration of the center of mass dotted with EX, which is equal to M1 A1I plus M2 A2I dotted with EX. So what does that give when we do that? This gives, well, I've got N EY plus M1 plus M2 G EY dotted with EX is equal to 0. And that has to equal M1 times X1 double dot EX plus M2 X1 double dot EX plus M2 X2 double dot little ex dotted with big Ex. Now if we do that, we see that 0, which is the left side, is equal to M1 plus M2 times X1 double dot, and then we have EX dotted with EX, and then we have plus M2 X2 double dot little ex dotted with big EX. Now you can see that, again, we wind up with a similar situation. We already have taken that before. That's equal to cosine beta. So this gives that 0 is equal to M1 plus M2 X1 double dot plus M2 X2 double dot times the cosine of beta, and this is the second differential equation. So our system of differential equations looks like this. First differential equation, which we already derived, is m2 x1 double dot cosine beta and then we have plus m2 x2 double dot, and then if we want to put everything on the same side, it's equal, we've got minus m2g times the sine of beta equals 0. And the other differential equation is m1 plus m2 x1 double dot plus m2 x2 double dot times the cosine of beta equals 0. That's our system of equations. Now, in order to finish this lecture, we're going to do a second example. So here's the second example. In the second example, we have a somewhat similar, but it's a very different setup in terms of what needs to be done. We have a wedge again, but this time the wedge has cut out of it a circle. It's a semicircle of radius r, and there's a particle that's sliding on the surface of this wedge, and the wedge is sliding on the ground. And once again, we're going to do something similar as far as measuring. What we're going to do is we're going to measure from a point here, which I'm going to call Q, and then we're going to call this point here P. This radius is R. This mass is little m, and I'm going to call the mass of the wedge big M. And we're measuring the position, so this has to be done a little bit more carefully because of the way things are marked, is that this distance is being measured from a point here, O, which is fixed to the ground. That distance, I'm going to call that distance Y. I'm not going to call it X this time. I'm going to call it Y. And then the angle that is from the vertical is the angle theta. And then gravity acts downward. And again, the objective is to determine the two differential equations, is to determine a system of two differential equations that describe the motion of the system. Now, how are we going to go about doing this? So we have to be more careful with the kinematics in this problem than we did in the previous problem, because you can see here that now we do have a rotation and we also have a translation. So the kinematics are going to be done as follows. Which is that we have one rotation, but we need the frames to be set up correctly. So the first frame is going to be the inertial frame. And actually, again, I equals the inertial frame. And then the second frame is going to be the wedge. And then there's going to be a third frame in this case. And the third frame is going to be, I'm going to call it A. And it's going to be the plane, which is out of page and then QP plane. And we'll get into the details of this in just a minute. The inertial frame, the coordinate system has its origin at O. I'm going to put EX, actually I'm going to put EY along OQ, and then EZ is going to be out of the page, and then EX is going to be EY crossed with EZ, so that the ordering is EX, EY, EZ. The next frame is going to be the wedge, and we strictly speaking don't really need the wedge, but it may be helpful. Actually, in this case, you know what? Let's just drop the wedge. We don't need the wedge. We're only going to use 2 frames. So the second frame is going to be the frame A, which is going to be, now I can define it as the EZ QP plane. We could have used the wedge, but it would have added an unnecessary amount of complexity because Y measures from O to Q. So we're going to put the origin of this coordinate system at Q. We're going to put ER along QP. EZ is going to be the same as big EZ, and then E theta is going to equal EZ crossed with ER. So you can see that the picture here looks as follows, is that this direction is, let's just move this down a little bit. This direction here is EY. This direction is EX. That direction is ER. And this direction is E sub theta. This angle is theta. This angle is theta. And then EZ is also the same thing as little ez. And that's going to be our setup. Now, we need to describe the position of each point. So let's actually do that. The position of, I'm going to call this big M, which is again measured relative to point O, is going to equal Y EY. The position of little m is equal to the position of big M plus the position of little m relative to big M. And that is equal to YEY plus RER. This is the position of little m, where you remember that I defined the radius to be capital R. So now let's get the velocity and acceleration. So the velocity of big M in the inertial frame is equal to y dot EY, and the acceleration of M in the inertial frame is equal to y double dot EY. Now we need to get the velocity and acceleration of the little mass, and so we have to be a little bit careful when we do that. So what we're going to do is I'm actually going to compute the velocity of little m relative to big M in the inertial frame. That's equal to the rate of change in the inertial frame of the position of little m relative to big M. But because that part of the vector is expressed in terms of a basis fixed in reference frame A, this is d dt in A of the position of little m relative to big M plus the angular velocity of A in the inertial frame crossed with the position of little m relative to big M. And that gives that the velocity of little m relative to big M in the inertial frame, the first term here is 0 because r is constant. We get theta dot Ez crossed with RER, which is equal to R theta dot E theta. So then the next thing I want is the acceleration of little m relative to big M in the inertial frame. That's equal to the rate of change in the inertial frame of the velocity of little m relative to big M in the inertial frame, which is equal to the rate of change in frame A of the velocity of little m relative to big M in the inertial frame, plus the angular velocity of A and I crossed with the velocity of little m relative to big M in I. Now, the rate of change in frame A of the velocity of little m relative to big M in I is equal to r theta double dot e theta, and the angular velocity of A in I crossed with the velocity of little m relative to big M in I is equal to theta dot Ez crossed with r theta dot e theta, which is equal to minus r theta dot squared er. So therefore, the acceleration of little m relative to big M in the inertial frame is equal to minus r theta dot squared er plus r theta double dot e theta, and therefore the acceleration of little m in I is equal to y double dot ey minus r theta dot squared er plus r theta double dot e sub theta. Okay, so that gives us the acceleration of both points in the both objects in the system. So now we have to go on and we have to do the kinetics. And again, the kinetics requires us to look at the various systems. So there are three possible systems. So we have to be really careful about this. Three possible systems. They are 1, the wedge, 2, the particle, and 3, the wedge plus the particle. Now, if we draw the free body diagrams of all of these, this is what we've got. Here's the wedge, and here's the free body diagram of the wedge. You can see that there's a normal force, there's the force of gravity, which is mg, and then there's the force exerted by this particle, which actually lies along this line ER, and I'm going to call that force F, M, M, which is the force exerted by little m on big M. Then there's the particle, and here's the particle. The forces exerted on the particle are the mass times gravity. That's the force of gravity acting on the particle. And then here is F little m big M, which is equal to minus F big M little m. And in order to make those m's a little bit more clear, let's actually write it like this. So we know the difference. And then there's the wedge plus the particle. And if we look at that system, here we have the wedge, and then here we have the particle. And you can see that the forces acting on this system are, there's a normal force, normal force, there's mg, and then here there's little m times g. Now, in order to be able to do this, we have to again do the same thing we did in the previous example, which is we have to pick one, either the particle or the wedge, and then pick the whole system. So we're going to choose these systems. So choose the following systems. 1, we're going to choose the particle because it has fewer forces acting on it. And 2, we're going to choose the wedge plus the particle because we have to choose the whole system. So now, if we apply Newton's second law to the particle, what does that say? It says the force exerted on the particle is equal to the mass of the particle times the acceleration of the particle in the inertial frame. Well, the force exerted on the particle is equal to what? Well, let's go back here. It's equal to the force exerted by the wedge on the particle, so F little m big M, and then plus, let's look what else is there, plus mg. Now, the force exerted by the wedge on the particle, because I don't know its direction, I'm going to say it's F big M. I don't know whether it's positive or negative. I know its line of action is along ER. And then I've got plus M, where does it say? Minus mg. Minus mg e. It's plus mg ex, the way we defined it. So let's go back over here and let's make sure that we define this consistent with our picture. Our picture has ex down, so it's plus mg plus mg ex. So that's the force, and that has to equal the mass times the acceleration of the particle, which is equal to y double dot ey minus r theta dot squared er plus r theta double dot e sub theta. So now we can look at this and we can see that this particular unknown force lies in the direction of er. So what we want to do is we want to take the scalar product in the e theta direction. And what does that do? When we do that, we get F little m dotted with e theta is equal to, well, we've got F little m big M er plus mg ex dotted with e theta, which is equal to, well, er dotted with e theta is 0, so you get mg ex dotted with e theta, and that is equal to the mass times y double dot ey minus r theta dot squared er plus r theta double dot e theta dotted with e theta. So if we look at the picture over here, we can see that ex, if I look at this picture, ex is equal to cosine theta er minus the sine of theta e theta. So ex is equal to cosine theta er minus the sine of theta e theta, which gives that ex dotted with e theta is equal to minus the sine of theta, and then ey is equal to, what's ey equal to? Ey is equal to sine theta er plus cosine theta e theta, which implies that ey dotted with e theta is equal to cosine of theta. And then we can substitute that in and we get minus mg times the sine of theta minus mg times the sine of theta, that's the left-hand side, is equal to m y double dot, and then ey dotted with e theta is equal to cosine of theta, and then er dotted with e theta is 0, and then e theta dotted with e theta is 1, so I get plus m r theta double dot, and that's the first differential equation. Now, let's look at the second system. So we did the particle. Now we're going to do the wedge plus the particle. So what do we get when we do the wedge plus the particle? This was the particle. So the wedge plus the particle says that the force exerted on the system is equal to the mass of the system times the acceleration of the center of mass of the system, which is also equal to m times the acceleration of big M in I plus little m times the acceleration of little m in I. Now, what's the force acting on the system? Let's look at the free body diagram. So the free body diagram says it's N plus M1 plus M2 times G, which is equal to N EX plus M1 plus M2G EX, where I note that, again, we don't know whether n is positive or negative, so I'm just going to put it in the positive direction. This then equals n plus m1 plus m2 times g, the whole thing times ex. And that has to equal the mass of the block, or the wedge, times y double dot ey, because that's the acceleration of the wedge, plus the mass of the particle times y double dot ey minus r theta dot squared er plus r theta double dot e sub theta. So now you can see that because n is in the direction of ex, we should take the scalar product in the ey direction. So what that means is we take f dotted with ey is equal to m times the acceleration of the wedge plus little m times the acceleration of the particle dotted with ey. Well, f dotted with ey is equal to 0 because all the forces act in the ex direction. Now if I take the mass of the wedge times the acceleration of the wedge in the inertial frame plus the mass of the particle times the acceleration of the particle in the inertial frame, and I dot that with ex, we obtain the following result. We have m y double dot ey, and then minus m r theta dot squared er plus m r theta double dot e theta, the whole thing dotted with ex, which is equal to, well, if you look at this, you'll see that since I'm taking the scalar product with ex, everything in the ey direction winds up dropping out. So I actually there's a term missing in here. Sorry, let's put that in here. This is equal to m plus little m times y double dot ey, where I forgot to include the little mass of the particle. So now if we take the scalar product with ey, we get minus mr theta dot squared er dotted with ex, and then plus mr theta double dot e theta dotted with ex. But we note that ex, we already had it from before. Ex is equal to cosine theta er minus sine theta e theta. So this gives minus mr theta dot squared. And then if we pull again, cosine theta er minus sine theta e theta. So we get cosine of theta. And then e theta dotted with ex. So we get minus the sine of theta. Minus mr theta double dot times the sine of theta. So this gives that 0 is equal to minus mr theta dot squared cosine of theta, and then minus mr theta double dot times the sine of theta. Where you notice that in this second expression, because the acceleration has components that are in EY, and then there are these other terms that involve ER and E theta, and I'm taking the scalar product in the direction of, we're taking the scalar product in the direction of EY, not EX. So this should be EY. Sorry about that. And then this should be EY. And if we take the scalar product, now we're doing all the scalar products with EY. So we should be writing EY. And this last part here actually changes to, we get ER dotted with EY, and EY was actually equal to sine theta ER plus cosine theta E theta. So this gives minus MR, and then there's another term in here that actually needs to be included, and this is equal to, and if we actually give ourselves again a little bit more room, so we've got M plus M times Y double dot, that's the first term, and now we can do the rest of these. So we wind up getting M plus M times Y double dot, and then ER dotted with EY. There's a sine theta component, so we get minus MR theta dot squared times the sine of theta, and then E theta dotted with EY. So EY again has a cosine theta component in the E theta direction, so I get plus MR theta double dot cosine of theta. So that gives us the second differential equation, and that says that because it has to equal 0, M plus M times Y double dot minus MR theta dot squared sine theta plus MR theta double dot cosine theta equals 0. So our system of differential equations looks as follows. The previous one was the one we got from we got my double dot cosine theta plus mr theta double dot plus mr theta double dot is equal to mg, and actually we can put all that again on one side, plus mg times the sine of theta, and that equals 0. And then the second differential equation is m plus little m times y double dot minus mr theta dot squared sine theta plus mr theta double dot cosine theta equals 0. So these are the two differential equations that arise from this. So in this lecture we were able to do two examples after describing the results of applying Newton's second law to each particle in a system of particles and then adding the results to be able to describe the resulting equation, which states that the force exerted on the system is equal to the mass of the system times the acceleration of the center of mass of the system. And then we use that result on two examples. And in future lectures, we're going to keep talking about systems of particles, and we're going to talk about other concepts such as angular momentum, and we will use the results from angular momentum to be able to describe motion of systems using that approach later on.